Okay, folks, so we're working through the pre-work for section 2.6 on continuity. And it should seem like some of the work we've done on continuity is similar to work we've done before, and that's because of what we're going to see in this next theorem here. It turns out that polynomial functions are continuous on minus infinity to infinity. That is, in terms of the lingo we gave last time, polynomial functions are continuous functions. They're continuous on the entire real number line. Rational functions are continuous wherever they are defined. This is simply a restatement of what property? We've actually saw something to this effect that said, hey, if we want to evaluate the limit as x approaches a of f of x, we could just say that that is f of a. When did we do this previously? Okay, so this is simply a restatement of some property. I'll let you go digging for that, except I'll tell you that it comes from section 2.3. It was a property that we presented in that class, or in that section. So if we want to evaluate the limit of some polynomial or rational function, if it's a polynomial function, we simply plug a into that, and we can evaluate the limit that way. Or if it's a rational function, as long as a is what? This is important. As long as a is in the domain of the function, then evaluating the limit and evaluating the function are the same thing. Okay. So in fact, we can extend this. That means this idea extends to the root, exponential, logarithmic, trig, and inverse trig functions. Those are all continuous on their domains, meaning from here on out, if I ask you to find the limit as x approaches a of f of x, and if it's one of these functions, a root function, an exponential function, logarithmic, trig, or inverse trig, if you want to evaluate that limit and the a value, this is the caveat, right? And the a value is in the domain of that function, then you can simply evaluate the function at that point. So this is an extension of the direct substitution property from section 2.3. Okay, so let's look at this function here. When is this function f of x equal to the cosine of x plus ln of x, all divided by x squared minus 9? When is this function continuous? Well, let's say a few things. The function cosine of x is continuous where? Well, we said that trig functions are continuous on their domains. What's the domain of the cosine function? Its domain is all real numbers. Okay, so when is the cosine function continuous? On all real numbers. Okay, the natural log of x is continuous where? Well, we said that the logarithmic functions, specifically the natural log, the logarithmic functions are continuous on their domains. What's the domain of the log function? As you'll see in your work this week, it's from 0 to infinity. That's its domain. So since the log function is continuous on its domain, it's continuous on 0 to infinity. When is x squared minus 9 continuous? Okay, now be careful here. I'm not asking a question about f yet. I'm building up to asking a question, when is f continuous? But I'm just asking you, if somebody handed you this function right here, f of x equals x squared minus 9, where is this function continuous? Well, it's a polynomial function, and what did we say? We said polynomial functions are continuous on minus infinity to infinity. Okay, so based on the work we did in the last video, we said, hey, if we take some sort of combination of functions through addition, subtraction, multiplication, or division, if they are continuous at a point, then so will the resulting function be. Provided, of course, if we're doing division, that the expression in the denominator isn't 0. So what I'm going to do is technically what the fancy phrase is, I'm intersecting these three domains to give me the domain where this function will be continuous. But one way of looking at it is you're saying, on what interval will all of these functions be continuous? And so this function f is continuous on the interval from 0 to 3, and again from 3 to infinity. Now pause the video and see if that makes sense. So certainly these three functions combined together through most ways would be continuous where? Well, wherever they're defined. Well, the natural log has the most restrictive domain. We can only consider positive values. So even though cosine is continuous and this polynomial is continuous elsewhere, natural log is only continuous on 0 to infinity. So at first you might think, okay, we'll give the answer as 0 to infinity. But what? Well, because in combining these functions together to create f of x, we introduce division, we've got to make sure that the denominator is non-zero. It won't be continuous where the denominator is 0, so we have to pluck out the 3, which is how we end up with this answer here. Don't worry about this for right now. We'll talk about this in class, but notice that I separated the two intervals with a comma. Okay. The next theorem we have states that limits pass through continuous functions. Okay? So what I'm saying here is, let's suppose we've got this function right here, f of x, I've got a composition of functions. I've got f of x, and sitting inside of f of x, I've got the function g of x. Okay? Well, if the inner limit exists, meaning the limit as x approaches a of f of x exists, and the outer function is continuous at that limit value, then this theorem says I can simply pass this limit through the continuous function. So that's what I'm showing here. I'm taking the limit as x approaches a of the composition of functions, and I'm passing that limit through the outermost function. Okay? The proof of this isn't too difficult, but it does require the precise definition of the limit, so we're not going to worry about proving that, although you'll get an insight in section 2.7. So this gives us some powerful tools. Okay, those two facts together, the fact that we can construct new continuous functions from old ones, and the fact that we can pass limits through continuous functions, allows us to evaluate some more challenging limits. Okay, so let's go ahead and look at this one here. We're being asked to evaluate the limit as x approaches pi. Okay, well, notice that the domain of this function, let's give this a name. F of x is equal to the sine of x all over 2 plus the cosine of x. The domain of this function is what? Well, the domain goes from minus infinity to infinity. How come? Well, the domain of the sine function is all real numbers. The domain of the cosine function is all real numbers. I'm adding together two functions. That doesn't change the domain. The only thing I'm potentially doing that could get me into trouble is I'm dividing. And I got to make sure I'm dividing by 0. Well, is there a way for 2 plus the cosine of x to ever be 0? What's the most negative y value that the cosine function can output? Well, the most negative y value that the cosine function can output is -1. If I added that -1 to 2, there's still no way to get a 0 in that denominator. So the domain of this function right here, the domain of f, is all real numbers. And it's built up of a composition of continuous functions. Composition. It's a combination of continuous functions. And so it's continuous wherever it's defined. And so we can simply evaluate this limit through direct substitution. So this is equal to the sine of pi all over 2 plus the cosine of pi, which is equal to 0 all over 2 plus -1, or 0 over -1, but that is just 0. So what we're saying here is, because this is a continuous function, and because pi is in the domain of that continuous function, then we can simply evaluate the limit through direct substitution. Okay? Now let's look at 19 here. 19 is a more interesting question. The domain of 19, let's see, the domain will be from minus infinity to -1, unioned with -1 to infinity. So the domain of this function is not all real numbers. Specifically, we're excluding -1, and that's precisely our limit value. Okay, so I cannot evaluate this limit through direct substitution. Notice that if I call this function g of x equals, actually let me give it a just kind of completely different name. Let's say j of x is equal to the sine of x squared minus 1 all over x plus 1. well, then j of x is not continuous at x equals negative 1. This entire function is not continuous at x equals negative 1. But what do we know about the sine function? I'm not talking about all of j of x, I'm just talking about the sine function. We know the sine function, it's a trig function, and it's continuous everywhere it's defined, and sines are defined at negative 1. So I'm using specifically theorem 17 here that says that limits pass through continuous functions. So since the sine function is continuous at x equals negative 1, I can rewrite this as the sine of the limit as x approaches negative 1 of x squared minus 1 over x plus 1. Let's look what I did here. I passed this limit through the sine function. Okay. Why could I do that? Normally I can't, but I knew that the sine function was continuous on all real numbers, so specifically it was continuous at negative 1, so I passed the limit through it. Okay, so now I'm going to continue. I'm just going to keep working this limit problem inside the sine function. So this is the limit as x approaches negative 1 of x plus 1 times x minus 1 all over x plus 1. We've actually worked this interior problem quite a few times. We can cancel out those two factors, and so we're left with the sine of the limit as x approaches negative 1 of x minus 1. But that's just the sine of, using direct substitution, negative 1 minus 1, or the sine of negative 2. And there is our answer. Okay? I'm not worried about getting a decimal approximation of that. It's kind of nicer just to leave it in exact form. But to close the loop on this, what did we do? We applied theorem 17, which says that limits pass through continuous functions. So even though this j of x, the function we're working with, isn't continuous at negative 1, I can't apply direct substitution to it. The outermost function was a continuous function, and so I passed the limit through that outermost function. So I'd like you to now try that. Try that with the question number 20 here with this natural log function. You're going to have to use this property. Okay, so put that in, practice that. But go ahead and give number 20 a shot on your own, and you'll get a chance to check with your neighbors in class tomorrow.